So this is a joint work with Serafina Lapenta and Giuseppe Mettere. It's a work in progress, so any feedback is particularly appreciated, as it may help us making it better. And the work goes back to the treatment of varieties with good ideals. Some classical sources are from the work of Orsini, and then jointly with Gumm and Aliano from the 70s. The main examples for this talk are the following ones. So take the variety of unital rings, then the ideals. So take a homomorphism between unital rings. You take the pre-image of 0. This will be a RNG, so a ring possibly lacking a unit. And these RNGs, in a certain sense, model the 0 ideals. Similarly, if you take Boolean algebras, which can be presented in the signature 0 join negation, for example, the 0 ideals are generalized Boolean algebras, which can be presented, for example, in the signature 0 join meet and the binary difference. The idea is that they are like Boolean algebras but without a top. For example, given any set, the finite subsets of X form a generalized Boolean algebra, but if X is infinite, it's not a Boolean algebra in general. Or if you know MV algebras, then they're the canonical, it's more standard to take 1 as constant to express ideals or filters in this terminology. Then you get what are called the Weisberg hoops. All right, so in this work, we want to focus on this question. So let's say you we have a variety of algebras, and like one of these, and we fix a certain constant. How do we get the algebras, the variety of algebras here? Like, what is a good choice of primitive operations? What are good axioms? For example, here, although the set difference, the binary difference, did not appear explicitly among the primitive function symbols of Boolean algebras, it is convenient to introduce them. All right. So first of all, let's see what is a good choice of primitive operations. Now, the fact is that on calling C the distinguished constant, on C ideals, the operations that are defined are those that are idempotent. So those that, when you apply C in all arguments, give you back C. For example, for rings, plus is 0 idempotent. Or in Boolean algebras, the difference is idempotent because 0 minus 0 is 0. But negation, for example, is not idempotent. And so that's why it doesn't appear in the signature of generalized Boolean algebras. So what we can take in principle is the clone of all 0 idempotent terms, but this is huge in general. So the question is, okay, when we can generate it in a small, by a small set, like for example, as it appears in rings or Boolean algebras. And here we will focus on a condition that is sufficient to reach this purpose, and which we call having swappable constants. Roughly speaking, Roughly speaking, it means that we can, all constants look the same and we can shift between them via unary terms. Okay, for example, in unital rings, if you take all the term-definable constants, and you identify those that are equal in all algebras, so for example, 1 minus 1 we identify with 0. This is a term-definable constants for are isomorphic to Z. And if you take, for example, any m in Z, I can shift between 0 and m via unary terms. I can translate it via plus m, and then go back with minus m. And these are mutually inverse. Or in Boolean algebras, something similar happens. So you have just two constants, two term-definable constants, 0 and 1, and the negation, let's say, shifts between them. Or the identity if you want to shift from 0 to itself. All right. So, so here, just to state the definitions, it will be of interest the initial algebra, so the algebra, the free algebra of the empty sets, so the algebra of term-definable constants, which for unital rings is Z, for Boolean algebras and MV algebras, it's the two-element set 0, 1. So this is the main definition we outlined, and which gives very good properties. We say that a variety has swappable constants. If for all term-definable constants C and D, there are these unary terms called shifts. Sigma from C to D. The notation should suggest that it maps C to D. And sigma from D to C, which are mutually inverse. So if you compose them in both directions, gives you a term which equals the identity. And that such that when you apply the first one to C, it gives you D. And consequently, since they're mutually inverse, when you apply the second one to D, it gives you C. So for example, for the unital rings, given any D, when fixing as C 0, I have the shift plus D, and with the inverse minus D. Or for Boolean algebras, I can shift using the negation. But more in general, if a variety has an abelian group reduct, then it has swappable constants. Because as sigma C plus D applied to X, I can take X plus D minus C. And as sigma D to C, X plus C minus D. So in particular, this abelian group reduct covers commutative rings, which have an abelian group reduct, and also Boolean algebras, which have an abelian group reduct. But there are examples where we have swappable constants without having an abelian group reduct. For example, MV algebras, which have no group reduct, where here the swaps are the negation, as just for Boolean algebras. More general, if a variety has swappable constant, then any subvariety. So if I add equations, I still have swappable constants. So, for example, every variety of MV algebras has swappable constants. A known example is Heyting algebras. Like here, the only constants are 0 and 1, if you're familiar with the MV algebras, and you can shift between the two with negation, but the negation is are not mutually inverse. So negation is not the identity. So that's the idea why what you would be tempted to do doesn't work. And in general, you can prove that it has no swappable constants. Essentially because when you have swappable constants, all constants look the same. So Also, when you have homomorphism to the initial algebra, in this case to 0, 1, the fibers have the same cardinality, and this does not happen for Lattice algebras. Okay, so this is the main definition I wanted to present, and let's see what we can do with it. So, what I find interesting is that in the clone of all C-idempotent terms, which might be huge, having swappable constant allows you to have a small generating set. So you take all, let's say you take all primitive operations of your variety, tau, and you make all possible conjugates by these shifts. Okay, so let's say T as RET n, then you take all possible tuples of constants, and you make the conjugates. So you first do sigma CT1, and so on. You apply tau, and then you go back. This is a C idempotent term, and the clone of these C idempotent terms is generated by this. Good. So, for example, Boolean algebras. Let's see how we get this negation. Well, you take the join, which is a primitive operation symbol of Boolean algebra, and then you make all possible conjugates. And for example, if you take the conjugates were with the 1 and 0, here you will plug in a negation, and then negation of the outside, and then you will get x and not y, which is x minus 4. Okay. And then these the slide before concerned the choice of the primitive operation symbols, but we also get an algorithm to impose the right equations. So just to have a criterion for checking that these are really the right equations, in the end we want to axiomatize these. Well, for example, here ideals are subreducts of rings. So we want to axiomatize subreducts obtained by just keeping the C idempotent terms up to term equivalence. And there's an algorithmic way to do this, starting from a presentation of the starting variety V, for example, of neutral rings or Boolean algebras. Essentially, you shift all actions of your variety, and then you take some bookkeeping equations. I have some more details in a better slides if you want, but what I want to convey is that, okay, there's an algorithmic way to do this. And moreover, for example, if your starting variety V has a finite equational basis, and you have only finitely many term-definable constants, then you get a finite equational axiomatization of this variety of C ideals.
What is capital boldface I here? You say finite equational basis?
All right. This is the I stands for initial. So I stands for initial object in the variety.
Okay, initial.
So the
algebra generated.
The empty generated free algebra. Okay.
Exactly. Thanks. Yes. That free algebra over empty set. Okay. Good. And finally, so for example, when you want to show that a commutative or a ring, possibly Latin unit, is the kernel of a certain homomorphism between rings with unit, one thing you can do is you construct out of A a certain ring with unit, which is a sort of semi-direct product between A and the algebra of constants. As a set is just the product, but the idea is that a pair AM should be A plus M 1, where this is the constant you want to introduce. And then you get back A as the kernel of the projection to the second coordinate. And this we can do it for whenever you have a swappable constant. You just use these shifted terms on the first coordinates. So these works for rings, works for Boolean algebras. If I have a generalized Boolean algebra, I can create a semi-direct product with 0, 1. And the idea is that x0 should represent x, while x1 should be not x. And to define how the semi-direct product acts here, you can just use these shifted terms, these conjugate terms. All right. Good. So, just a final remark. Now, this C ideal, this variety here, in a certain sense, is canonical. First of all, because it's term equivalent to the variety of subreducts. So the class, which one can show to be a variety of subreducts of V with respect to the signature of both C and potent terms. Okay, but if you want also to remove the dependency on C, this is also equivalent to something that does not depend even on C, which is the slice category over the algebra of constants. The slice category has as object, well, this morphism from A in your variety to, in this case, the initial algebra. So, for example, for rings, it's a category whose objects are morphism to Z. And given one such morphism, we get a C ideal by taking the preimage. And the other direction, you use this semi-direct product construction, where to a C ideal you take this semi-direct product with a projection from the second coordinate. Okay? So in conclusion, fixing a variety V and a term-definable constant C, if, we get a concrete signature and a concrete equation of axiomatization for the variety of C ideals of V. And this equals to two things that appear probably more canonical, which is the class of subreducts of V with respect to the clone of C idempotent terms, but also to this slice category. And these shifts allow to have a manageable representation. And also we get a semi-direct product construction. And just to give more context on this work, actually we started because we were interested in when this slice category coincide with the class of subreducts of V with respect to the class of C idempotent terms. We got a Maltsev-like condition similar to classical C ideal determined varieties, if you know what that means. But then all natural examples we had satisfied these swappable constants. So in this talk I focused of this property. Thank you.